of radius ratio rule. Limitations of radius ratio rule. Okay. Radius ratio provided correct structure in many cases such as NaCl, CaCl. Okay, and ZnS. Okay. Radius ratio provides correct structure in many cases such as NaCl, CaCl, ZnS. But in many cases, it also predicts the wrong structures, hence it does not provide a completely reliable method for predicting the actual structure of ionic solid. The main limitations of radio ratios rule are as follows. First point, values for ionic radii cannot be determined absolutely, but are estimated. They are not completely accurate or reliable. The interionic distance between two different ions can be measured by X-ray crystallography. Okay, X-ray crystallography. Okay. It is much less certain how to divide the distance between two ions to obtain ionic radii. Thus, accurate ionic radii are not known. In addition to this, ionic radii are not constant but change depending on its environment. By increasing coordination number, ionic radii increase and vice versa. Okay? If increasing coordination number, increasing coordination number. By increasing coordination number, ionic radii increases. Ionic radii increases and vice versa. Okay. Second point. An ion is treated as a sphere is that ions are spherical in shape. This far from reality errors will appear if anions get polarized and bonding has some partial covalent characters. Example, radius ratio for AgL is 0.52, which is indicating the coordination number is 6, but actually it is 4 coordinated. Third point. Some compounds may exist in more than one modification with a different coordination number due to anion repulsion. The internuclear distance would be different. Okay. Next point. Point 4. Bonding is not 100% ionic in ionic solids. Bonding is not 100%. Bonding is not 100%. Bonding is not 100% ionic. 100% ionic or ionic in ionic solid. Ionic solid. Okay. Bonding is not 100% ionic in ionic solid. There is a small contribution of covalent bonding also. Fifth point. Okay. Ions do not behave as a hard inelastic. Sphere. They are sometimes fitted into holes that are slightly too small, due to which the ions are compressed. Thus, distortion produces in the crystal lattice. Okay. Sixth point. As the radius of occasion is greatly influenced by the anions due to polarization. That is why covalent character develops in ionic solids and radius changes. Such type of ionic crystal do not obey radius ratio rule. Seventh point. Stable arrangements are only possible if the cations and anions touch one another, but this is not always valid. Okay? Stable arrangements are only possible if the cations and anions touch one another, but this is not always valid. As the above condition do not meet always, has the radius ratio values do not predict correct geometry. Always radius ratio often predict the correct structure, but they do not always predict the correct structures. Okay. Coordination number CN. Coordination number. Coordination. Coordination number. Coordination number. Okay. Coordination number. What is coordination number? We will be knowing about coordination number, shear number. Okay. What is shear number? How to use shear number? Okay. What is the information about coordination number? All totally we will be studies in this heading. Okay. In ionic solid, cations are surrounded by anions. In ionic solid, cations is surrounded by anions. Cations is surrounded by anions. Okay. In ionic solid, cations are surrounded by anions and vice versa. The number of ions of opposite charge. The number of ions of opposite charge surrounding an ion in the ionic solid is called coordination number. It is denoted by Cn. Okay. How to define the Cn? The number of ions. The number of opposite charge. The number of ions of opposite charge surrounding in the number of opposite charge surrounding an ion in the ionic solid is called coordination number. It's called coordination number. Okay. It's called coordination number. It is denoted by Cn. The number of ions of opposite charge surrounding an ion in the ionic solids. The number of ions of opposite charge surrounding in ion the ionic solid is called coordination number Cn. Okay. In case of ionic crystal of AX type, as example, sodium chloride NaCl, CaCl, and ZnS etc. In which the number of each kinds of ion is same. The coordination number of cations is same as that of anions. In NaCl, the coordination number of Na plus and Cl negative ions is 6. Thus the Na cations, Na positive ions is surrounding by 6 Cl negative ions. NaC, that is sodium positive ion. Sodium positive ion is surrounded by 6 Cl 6 chlorine negative ions. Okay, and similarly each chlorine negative ions is also surrounded by 6 sodium ions, surrounded by 6 sodium ions in case AX2 or A2X. In case AX2 or A2X. In case AX2 or A2X, ionic crystal, the CN coordination number of cations is different from that of anions in CaF2. In CaF2, the number of fluorine negative ions, is twice as that of calcium positive ions. From X-ray study, it is clear that coordination number of calcium positive 2 and fluorine negative ions are 8 and 4 respectively. Okay? This is the coordination number, and some typical ionic structure. We will be studying about some typical ionic structure. Okay? In AX type, structure of ionic solids of general formula AX. Okay? In AX type ionic solid, the coordination number of positive ions and negative ions, cations and anions are similar. In AX type structure, ionic solid, the coordination number of positive ions, that means cations are equal to the negative ions, CN number of negative ions. Okay? Similar. This is because of electroneutrality of the ionic solid or crystal. The structure of a sodium chloride, CaCl, ZnS, and typical examples AX-type ionic compounds. These three compounds represent three different types of general structure arrangements. Okay, first ionic structure of solid sodium chloride. First is ionic structure of sodium chloride. In NaCl, the radius of cations, Na positive ions. In NaCl, the radius of cations is 0.95 angstrom, and the anions and the radius of anions is 1.81 angstrom. Okay, thus the radius ratio R Na positive ions upon R Cl negative ions is 0.524, which lie between 0.414 to 0.732. Thus the coordination number should be coordination number 4R6. Okay. From the X-ray study, it is clear that sodium chloride has an octahedral structure. Octahedral structures. Okay. From the X-ray study, it is clear that sodium chloride has an octahedral structure. Each sodium ion is surrounded by 6 chlorine ions. Each sodium sodium ions is surrounded by 6 chlorine ions. 6 chlorine ions at the corner of the rectangular octahedral. Of the corner of the rectangular octahedral, and similarly each chlorine ion is surrounded by each chlorine ion is surrounded by 6 sodium ions. 6 sodium ions has coordination number of Na positive ions and Cl negative ions is thus 6. Is thus 6:6. The sodium chloride structure has been shown. You can see also this figure. And in sodium chloride, the cations and anions are in face-centered cubic FCC arrangement. Okay. In cation and anion. In cation and anion are face-centered cubic. Centered cubic, that is FCC arrangement. Okay. And it is also treated as a cubic closed packed array of chlorine negative ions in which sodium positive ions occupy the octahedral holes. There are 6 octahedral holes around each chlorine ions, and each chlorine ion is also surrounding by 6 sodium positive ions. Hence, the rock salt structure is called 6:6 coordination. Number 6:6 coordination. Number 6:6 coordination number. Okay. Coordination structures. The unit cell of sodium chloride has 4 positive ions and 4 chlorine ions, which is calculated as follows. Number of sodium ions. Number of sodium ions is 8 at corners. Multiply 1 by 8 plus 6 at face centered plus 6 at face centered multiply 1 by 2, that is 1 plus 3, that is 4, and number of chlorine ions. And number of chlorine ions is 12 at edge centered. 12 at number of chlorine ions is 12 at face centered. 12 at edge centered. 12 at edge centered. 12 at edge centered. Cross 1 by 4 plus 1 at body centered. 1 at body centered. Cross 1. That is 3 plus 1 equal to 4. 3 plus 1 equal to 4. Okay. Thus, number of sodium chloride units per unit cell is 4. For each chlorine ion, there is 1 sodium ion. This fulfills the stoichiometry of sodium positive ions or chlorine negative ions. Also, the structure of sodium chloride is also called as a rock salt structure. The structure of sodium chloride is also called as a rock salt structure. The ionic structure of sodium NaCl, NaI, sodium iodide, KCl, potassium chloride, magnesium oxide, MgO, FeO, etc. have also sodium chloride-like structures. Second point, structure of cesium chloride. Structure of cesium